In the last couple videos, I showed how you can take a function, just a function with two inputs, and find the tangent plane to its graph. And the way that you think about this, you first find a point, some kind of input point, which is, I'll just write abstractly as x naught and y naught. And then you see where that point ends up on the graph, and you want to find a new function which we were calling L, and maybe you say L sub f, which also is a function of x and y. And you want the graph of that function to be a plane tangent to the graph. Now this often goes by another name. This will go under the name local linearization. Local linearization. It's kind of a long word. Zation. And what this basically means, the word local means you're looking at a specific input point. So in this case, it's at a specific input point, x naught, y naught. And the idea of a linearization means you're approximating the function with something simpler, with something that's actually linear. And I'll tell you what I mean by linear in just a moment. But the whole idea here is that we don't really care about, tangent planes in an abstract 3D space to some kind of graph. The whole reason for doing this is that this is a really good way to approximate a function, which is potentially a very complicated function, with something that's much easier, something that has constant partial derivatives. Now, my goal of this video is going to be to show how we write this local linearization here in vector form, because it'll be both more compact and hopefully easier to remember, and also it's more general. It'll apply to things that have more than just two input variables like this one does. So just to remind us of where we were and what we got to in the last couple videos, I'll write it a little bit more abstractly this time rather than a specific example. The way you do this local linearization is first you find the partial derivative of f with respect to x, which I'll write with the subscript notation, and you evaluate that at x sub o, or x naught, y naught. You evaluate it at the point about which you're approximating, and then you multiply that by x minus that constant. So the only variable right here, everything is a constant, but the only variable part is that x. And then we add to that, basically doing the same thing with y. You take the partial derivative with respect to y, you evaluate it at the input point, the point about which you are linearizing, and then you multiply it by y minus y sub o. And then to this entire thing, because you want to make sure that when you evaluate this function at the input point itself, you see when you plug in x naught and y naught, this term goes to 0 because x naught minus x naught is 0. This term goes to 0. And this is the whole reason we kind of paired up these terms and organized the constants in this way. This way you can just think about adding whatever the function itself evaluates to at that point. And this will ensure that your linearization actually equals the function itself at the local point. Because hopefully if you're approximating it near a point, then at that point it's actually equal. So what do I mean by this word linear? The word linear has a very precise formulation, especially in the context of linear algebra. And admittedly, this is not actually a linear function in the technical sense. But loosely what it means, and the reason people will call it linear, is that this x term here, this variable term, doesn't have anything fancy going on with it. It's just being multiplied by a constant. And similarly, this y term, it's just being multiplied by a constant. It's not squared, there's no square root, it's not in an exponent or anything like that. And although there is a more technical meaning of the word linear, this is all it really means in this context. This is all you need to think about. Each variable is just multiplied by a constant. Now you might see this in a more complicated form, or what's at first a more complicated form, using vectors. So first of all, let's think about how we would start describing everything going on here with vectors. So the input, rather than talking about the input as being a pair of points, what I want to say is that there's some vector that has these as its components, and we just want to capture that all, and I want to give that a name. And kind of unfortunately, the name that we give this, it's very common to just call it x, and maybe a bold-faced x, and that would be easier to do typing than it is writing. So I'll just kind of try to emphasize bold-faced x equals this vector, and where that's confusing because x is already one of the input variables that's just a number. But I'll try to emphasize it, just making it bold. You'll see this in writing a lot. X is this input vector. And then similarly, the specified input about which we are approximating, you would call, let's say I'll make it a nice bold-faced x naught. We'll do that naught to just kind of indicate that it's a constant of some kind. And what that is, it's a vector containing the two numbers, x naught, y naught. So this is just our starting to write things in a more vectorized way. And the convenience here is that then if you're dealing with a function with 3 input variables or 4 or 100, you could still just write it as this bold-faced x with the understanding that the vector has a lot more components. So now let's take a look at these first two terms in our linearization. We can start thinking of this as a dot product, actually. So let me first just kind of move this guy out of the way and give ourselves some room. So he's going to just go up there, just the same guy. And now I want to think about writing this other term here as a dot product. And what that looks like is we have the two partial derivatives, f sub x and f sub y, indicating the partial derivatives with respect to x and y. And each one of them is evaluated, let's see, I'll do it evaluating at our bold-faced x naught. And then this one is also evaluated at that bold-faced x naught. So really you're thinking about this as being, a vector that contains two different variables. You're just packing it into a single symbol. And the dot product here is against, the first component is x minus x naught. So I'd write that as x minus x naught, the number, and then similarly y minus, let's see, I'll do it in the same color, y naught, the number. But we can write each one of these in a more compact form, where this, the vector that has the partial derivatives, that's the gradient. And if that feels unfamiliar, maybe go back and check out the videos on the gradient. But this whole vector is basically just saying take the gradient and evaluate it at that vector input, x naught. And then the second component here, that's telling you you've got x and y minus x naught, y naught. So what you're basically doing is taking the bold-faced input, the variable vector x, and then you're subtracting off x naught, where x naught is some kind of constant. So this right here, this is just vector terms where you're thinking of this as being a vector with two components and this one is a vector with two components. But if your function happened to be something more complicated with, 100 input variables, this would be the same thing you write down. You would just understand that when you expand this, there's going to be 100 different components in the vector. And this is what a linear term looks like in vector terminology, because this dot product is telling you that all of the components of that bold-faced x vector, that expands into, not bold-faced x, y, z, whatever else it expands to, all of those are just being multiplied by some kind of constant. So we take that whole thing, that's how you simplify the first couple terms here, and then of course we just add on the value of the function itself. So you would take that as the linear term, and I kind of like to add it on to the front actually, where you think about taking the function itself and evaluating it at that constant input, x naught. Because that way you can kind of think this is your constant term, this is your constant term, and then the rest of the stuff here is your linear term. The rest of your stuff is your linear. Because later on, if we start adding other terms, like a quadratic term or more complicated things, you can kind of keep adding them on the end. So this right here is the expression that you will often see for the local linearization. And the only place where the actual variable shows up, the variable vector, is right here, is this guy. Because, when you evaluate the function f at a specified input, that's just a constant. When you evaluate the gradient at that input, it's just a constant. And we're subtracting off that specified input, that's just a constant. So this is the only place where your variable shows up. So once all is said and done, and once you do your computations, this is a very simple function. And the important part is maybe this is much simpler than the function f itself, which allows you to, maybe compute something more quickly if you're writing a program that needs to, deal with some kind of complicated function, but runtime is an issue. Or maybe it's a function that you never knew in the first place, but you were able to approximate its value at a point and approximate its gradient. So this is what lets you approximate the function as a whole near that point. So again, this might look very abstract, but if you just kind of unravel everything and think back to where it came from and look at the specific example of a, tangent plane, hopefully it all makes a little bit of sense, and you see that this is really just the simplest possible function that evaluates to the same value as f when you input this point, and whose partial derivatives all evaluate to the same values as those of f at that specified point. And if you want to see more examples of this and what it looks like and maybe how you can use it to approximate certain functions, I have an article on that you can go check out, and it would be particularly good to kind of go in with a piece of paper and sort of work through the examples yourself as you work through it. And with that said, I will see you next video.